Chemistry, the Central Science, Chapter 6, Electronic Structure of Atoms, Lesson 2. So let's talk about Bohr's theory of the hydrogen atom. So what we have here is a gas discharge tube, which has hydrogen in it, and it's hooked up to a high voltage source, which basically means electricity is allowed to current through the gas. So what happens when we see this? Well, when we just look at it, it glows pink. Well, what if we look through a spectroscope and separate the light into its components? Well, then we see the line spectrum for hydrogen. So this is unique to hydrogen. It will always come off as these specific wavelengths of colors because these specific wavelengths are associated with allowable energy transitions for that one electron that hydrogen has. So electromagnetic spectra is unique for every element. If you get an element into its gaseous state, you hook it up to a high voltage source, we can see what colors are associated with each of these elements. So sodium is very typical with its yellow. When there were sodium lamps, they always glowed yellow. Potassium, when you burn it, it's kind of a light purplish color. Calcium tends to burn red. As we go through here, we know typical neon, right? Neon lights that we see, why are they glowing that specific color? Typically neon glows orange. If you put different types of gases into those tubes, that's how we get the different colors of our, quote, neon lights. But each of these are unique. Each of these lines is representing a specific energy transition that an electron takes, and we know that energy is related to both the frequency and the wavelength of light. These are specific, they do not change for each individual element. So, Bohr's model of the atom, and we studied hydrogen because it is a one electron system, so we don't end up with multiple transitions happening with multiple electrons at one time. So the electron, when there's energy available, it's going to bounce around. It's going to jump up and jump down and relax, and it just depends on how much potential there is, right? What is the energy source that's allowed? So the energy of a specific level, when we look at this, is based off of what we call the quantum number, the principal quantum number, which says n equals 1, n equals 2, n equals 3. These are always integer values, and these are the allowable states for an electron to exist in. So our electrons can't just tunnel into the nucleus. They are allowed to be at specific distances or specific energy levels away from the nucleus. And that energy is determined by this equation. So light is always emitted when the electron is relaxing. So it's going from a higher energy level to a lower energy level. And this, once again, is just showing how energy for electrons are quantized when they are transitioning between energy levels. So another way to look at this is stairs on a staircase, right? So here we're showing the ground state, which would be n equals 1, n equals 2, 3, 4, 5, 6. So the first thing that we want to pay attention to is that as we move farther away from the nucleus, the energy levels get closer and closer to each other. So that means that an energy transition from higher levels into higher levels is going to be lower in energy than to lower levels. So we can see here, right, a green wavelength of light is higher in energy than a red wavelength of light. But this is the allowable transition. We can go in between stair steps, right, on top of a stair step to another, but we cannot exist in the middle. We're either on a level or on a different level, period. So just like stairs or rungs on a ladder, you cannot exist between them. You have to be on the ladder, on one of the rungs, on one of the stair steps. So what's important also to pay attention to is that if we wanted to excite this electron and go the opposite way, it would be the same amount of energy and the same color of light that is associated with that. So once again, we're just thinking about energy in terms of it's a fixed value for a specific transition. I absorb a certain amount of energy, I can excite my electron in a special way. I give off that same amount of energy, my electron relaxes in the same way. So the emission spectrum of hydrogen, like I say, we studied this one because it was the easiest to study because it's a one electron atom. So we have this series that are named after scientists who studied them, right? So Lyman is always transitioning to n equals 1. Balmer is transitioning to n equals 2, Paschen n equals 3, Brackett n equals 4. So it's within the Balmer series that we actually see the visible colors of light. Here we're at too high of an energy to actually see that. That would be on the UV side, right? And on this side, then we're in the infrared side. So we can't see infrared, we can't see UV radiation. So looking at this, if we wanted to figure out what our energy transition was, we know that it's delta E, which is the state function, is EF minus EI. Well, if we set up our constraints here with our specific constants, so things cancel out, if we combine this, delta E then becomes our fixed constant here, which we talked about on a previous slide. It's 2.18 times 10 to the negative 18th joules. That's multiplied by 1 over the final energy state squared minus 1 over the initial energy state squared. This equation can also be rearranged to solve for a wavelength. 1 over the wavelength equals the Rydberg constant here, multiplied by this as long as your final state is lower in energy than your initial state. So we can use this equation to basically calculate energy transitions for a hydrogen electron. So for the hydrogen atom, calculate the wavelength of an emitted photon in the Lyman series that results from the transition n equals 3 to n equals 1. So we have our equation here. We're recognizing that we're going from and to. So our initial is n equals 3, our final is n equals 1. So we have the 1 here and the 3 here. We want to be careful and not to try and combine like terms as a denominator. You're not allowed to do that. So we can't just say 1 over 1 minus 9, right? That's not the way that works. It's 1 divided by 1 minus 1 divided by 9. That's how we get to this value. Multiply these two together. We end up with an energy of the transition, negative 1.94 times 10 to the negative 18th joules. So it asks for the wavelength. So then we are going to use our equation E equals hc over nu. Plugging in respective values, we just calculated the energy. Here we said the energy is negative. Well, why did we make it positive down here? It's negative because our electron is relaxing. So it's giving off this amount of energy. That's what the negative sign means. However, if we were to use the negative sign down here, we would end up calculating a negative wavelength, and that's not allowed. So when you calculate an energy transition and you want to find the wavelength, you just make your energy positive because it is the absolute value of the energy that tells you what the frequency or what the wavelength is. So to solve for wavelength, I'm multiplying Planck's constant times the speed of light and then dividing by the energy. So that's how I get to 1.03 times 10 to the negative 7th meters. If we put that, if we convert that into nanometers, we see that is 103 nanometers, and that is on the UV range of spectrum of light. So this problem is a little different. What if we know the energy transition, but we want to know how the transition is occurring? So the energy for an emitted photon is 7.57 times 10 to the negative 20th joules. If we start at n equals 6, what is our final value? What is the energy level that the electron rests at? So once again, I'm using the same equation. I have my energy, so I'm going to plug that in over here. It says that the energy of an emitted photon, so that means that it's being given off. That is why I make it negative. So I divide my negative 2.18 times 10 to the negative 18th joules into negative 7.57 times 10 to the negative 20th joules. That gives me 0.0347 equals 1 over my final energy state squared minus 1 over 36. Because we plugged in our initial state, 6 over here, so 1 over 36 is how I got this. So continuing to do the math then, I'm going to put this in my calculator. That comes out to a value of 0.0278. I need to get NF squared by itself, so I add the 0.0278 to this side. That comes out to 0.0625. To solve for NF squared, I'm going to switch places here. So 1 divided by 0.0625 equals 16. So NF squared is 16. If I take the square root of both sides of the equation, I get that my final energy state was equal to 4. So this tells me that when an electron transitions from n equals 6 to n equal 4, the energy that is associated with that is 7.57 times 10 to the negative 20th joules. So we've talked about, from Einstein's photoelectric effect, how there's that dual nature to an electron. It behaves as a wave, it behaves as a particle. So if we look at this in terms of the circumference of a circle, right, 2 pi r equals n, which is your principal quantum number, times some wavelength. So once again, your n has to be 1, 2, 3, 4, right, a whole integer value. This is looking at wavelengths over here, right? We need to make sure that we are confined to a specific circumference that the electron can be in, such that the waves do not eventually just diminish, right? They would start to cancel each other out, and then the electron tunnels into the nucleus. That is not going to happen. So we only have our allowable energy states such that these waves do not cancel each other out. There is no destructive interference then. So we can figure out the wavelength of anything else that has mass and velocity, because we know electrons are traveling at the speed of light. We know the mass of an electron. So we can look at wavelengths of light for anything else that has mass and is traveling at a velocity using Planck's constant. And that is called a de Broglie wavelength. So if the de Broglie wavelength of an electron is 44 nanometers, what is its velocity? And the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So we're using our equation here that says wavelength equals Planck's constant divided by the mass times the velocity. So we have to make sure that we're paying attention to units, which means that we need things in meters, kilograms, and seconds. So we're going to convert our wavelength of light by dividing by 1 times 10 to the 9th to get 4.4 times 10 to the negative 8th meters. So that's that's the wavelength of this particular electron. We're plugging it into our equation here. This is Planck's constant. Here's the mass. We're solving for velocity. We remind ourselves that a joule is a kilogram meter squared per second squared. So that's how we're able to cancel out units. So if I substitute in those units for a joule, I see that my kilograms cancel, one of my meters cancels, one of my seconds cancels. Therefore, I end up with meters per second. So 6.626 times 10 to the negative 34 divided by the product of our mass and our wavelength gives us a speed of 1,600 meters per second. So for a proton, where we know that the mass is about 10,000 times bigger, that moves with a velocity of 2.83 times 10 to the 4th meters per second, what is the de Broglie wavelength in nanometers? So once again, we're using our de Broglie wavelength equation. We have our velocity, we have our mass, it is in the correct units. We have our Planck's constant. So once again, we take the units of joules and turn them into kilogram meters squared per second squared so that our units will cancel out. So kilograms cancels, meter cancels with the meter here, seconds and seconds cancel out with our seconds squared. So we're dividing Planck's constant by the product of our mass times our velocity, which gives us a wavelength of 2.57 times 10 to the negative 8 meters. So down here, if we convert that back into nanometers, we see that we're multiplying by 10 to the 9th, which tells us then that our wavelength is 25.7 nanometers. So extremely small wavelength, extremely high energy, and a high frequency, right? So the last bit of this section, we'll talk an intro to quantum mechanics. So basically what happened was classical physics failed us in trying to describe the behavior of electrons because they move so quickly and they travel as a wave, which classical mechanics does not allow a good description for, right? Newtonian physics. So Heisenberg came up with this uncertainty principle, which says that at any moment, you cannot know both the exact location and the exact momentum of an electron. So you can know one or the other to a high degree of accuracy, but once you start pinpointing one of them, then the uncertainty grows significantly in your other value that you're trying to measure. So Heisenberg's uncertainty principle is given here. So it's based off of Planck's constant and pi, right? Because we're talking about allowable energy levels for a specific electron. So with this, if we imagine, racing cars, we can know where the car is, who crosses the finish line first, right? By a photo finish. We take a picture and we can see which car crossed the line first, right? That would be knowing the car's exact position. If instead we were measuring the speed of the car as it crossed the line, that would be done with a radar gun, right? And the measurements themselves are completely different because measuring speed says you have to measure a change in distance over a change in time. So we can't both take the picture, i.e. photo finish, and have a radar gun for an electron because an electron is so small, right? At a car, it's very easy to do these things because we can see them, right? We can see the car, we can see it past the finish line. We could look at what the speed was. But for an electron that is so small and moving so fast, basically this is just telling us when we are making measurements and studying these things, whether it be position or momentum, the observation of it itself is going to affect other observable properties. So I can know the location, but if I know the location, I can't know the momentum. If I know the momentum, I can't know the location at the same time. So it's all about your perspective on what are you studying, what are the mathematical observations that you're doing, and what are the results from those.